Hello everyone. In this lecture, we will learn what is AVL tree, why it is needed, and how it's implemented in data structures. As an overview, we will have a look at the definition of AVL tree, explanation of height in AVL tree, explanation of balance factor in AVL tree, and explanation of rotations in AVL tree. AVL tree is named after their inventors George Adelson Welsky and Evgeny Landis. It is a binary search tree that is developed to ensure big O log n time complexity at any given moment for the required actions, such as insert, search, and delete operations. To acquire this time complexity, AVL tree balances itself with a proposed method. The method checks if the left and right subtree height difference is not more than 1 or less than -1 after each operation call. This check is so often called the balance factor. So if the balance factor is less than -1 or more than +1, the proposed balancing methods perform some rotations in the binary search tree to keep the binary search tree in balance and in valid form. There are two important properties of AVL tree that we need to pay attention. First one is height. Height variable in AVL tree is used to store height of each node individually in the AVL tree. Theoretically, this can be calculated by counting edges from a specific node to the furthest descendant node. This can be seen in the example below. As you see, key 95 has 0 height since it doesn't have any other node that it is pointing at. Same as key 33, which also has the height of 0. Node with key value of 90 has height of 1 because it has one node that is connected, which is 95. Node 40 has height of 2 because its furthest descendant node is 95, and from 40 to 95 there are two edges that is connected. Second is the balance factor. Balance factor determines whether the AVL tree is in a balanced form and rotate the tree if otherwise. Balance factor from a node can be calculated by taking the difference of height of left subtree minus height of right subtree. The result coming from a balance factor can be used to validate if the recent form of the AVL tree is balanced. Valid balance factors for a given AVL tree are -1 means that the right subtree is higher by 1 than the right subtree, 0 means that the left subtree and right subtree are balanced or they have equal heights, 1 means that the left subtree is higher by 1 than the right subtree. If number that is returned from balance factor calculation is lesser than -1 or bigger than +1, required rotations will be applied to balance the tree. In the next slide, let's look at the example how all described properties are applied in more practical solutions. From the given tree, we have 40 as our root node, 33 at left subtree and 90 at right subtree. Node 90 and 30 have height of 0. This means they are not pointing at any neighboring additional nodes. And 40 has height of 1 because the furthest descendant node from 40 would return only height of 1. Let's go on and see how height and balance factor would change when we add another node with a key in our AVL tree. Let's add node with key value of 24. It would be located at the left subtree of 33. We should pay attention that latest added node will always have height of 0 as default height. This makes sense because latest added node will always have null pointers. After addition of node 24, we update the height and check the balance factor until we reach the root node. Node with key value of 33 will now have height of 1, and 40 will have height of 2 now because the furthest descendant node from 40 is 24. After recalculating heights, we can now check the balance factor for each node to validate our AVL tree. In this example, please keep in mind that the order of calculation for height and balance factor is not same as how calculations are ordered at the implementation of insertion method on Java. We will see how height and balance factor calculations are ordered using recursive approach at the next lecture with a practical example. But for now, it is convenient to show the calculations with my specific order for better understanding. So this said, let's go on and calculate balance factor starting from the latest added node. We know that the balance factor is equal to height of left subtree minus height of right subtree. We also know that null pointer from a node returns -1. So from the formula, we can find the balance factor for the node 24. 24's left pointer is null, which will be returning -1. And right pointer is also null, which also will return -1. -1 minus -1 will be equal to 0, which doesn't violate our AVL tree. So we go next. Note with a key value of 33, again, height of left subtree of a node 33 is 0, and right pointer of 33 is null, which will return -1. So 0 minus -1 will be equal to +1, so it also doesn't violate our AVL tree. Next, the root node with key value of 40, height of left subtree is 1, and height of right subtree is 0. 1 minus 0 is equal to 1. So at this current state, we have a valid AVL tree, which is also a balanced tree. So let's do something different and try to break our tree to return invalid balance factor value. To do that, I will add another node with key value of 14. It will have default height of 0 and predecessor node's height will be updated. Node 24 now will have height of 1. Node 33 will have height of 2. And root node will have height of 3. Next, we calculate the balance factor. Node 14 will return balance factor of 0. Node 24 will return balance factor of 1. And when we are at the node with the key value of 33, we have a violation. It is because the difference between height of left subtree and height of right subtree from node 33 returns 2, because 1 minus -1 is equal to +2. So as we remember, to have a valid tree, we need to have balance factor of -1, 0, or 1. And any number exceeding these values will mean that our AVL tree is unbalanced. So what do we do then? So we do rotations. There are 4 types of cases and corresponding rotations in AVL tree. The first one, which we encountered just in the previous example, is the left-left case, which requires to make right rotation to balance our AVL tree. Theoretically, we can determine the case by looking at the pointer from the node that the unbalancing has occurred and go down until the latest added node. Node 33 is the node that the unbalancing has occurred, and the latest added node is 14. So from 33 to 14, we go 2 times left. This is why the cases actually are named in AVL tree. As you can see, we have left from 33 to 24 and left pointer from 24 to 14. So its naming convention for the case makes sense now as left and left case. We know that in left-left case, we need to make right rotation. To illustrate this rotation, imagine that there's a hinge just beneath the node 33. Then 33 would go right down and all other connected nodes would go up. We change the pointer of new hinge node to the right and now it points to 33. We update the heights of nodes after rotation until we reach the root node and root node included. So after update, we now have balanced tree with given heights. You can check the validation by calculating balance factor from each node. At next, let's add additional nodes with key values to populate our AVL tree and see other cases. Starting with node 98, it will be located at the right pointer of node 90. And node 120, which will be located at the right of node 98. After adding 120, we update the heights and calculate the balance factor. Node with key value of 90 now will have balance factor of -2, because -1 minus +1 is equal to -2. This violates our valid AVL tree definition. To make AVL tree a valid and balanced AVL tree, we need to check our case and perform the required rotation. In this situation, we have right-right case which requires left rotation. So let's see how left rotation would reformate our AVL tree. Again, let's assume that there is a hinge beneath node 90 this time. We pull the node 90 down to left and connected nodes goes up. Hinge node 90's left pointer now points at 90. We update the heights and now we have a valid AVL tree. Now let's take a break and look at our AVL tree. We should notice that AVL tree also doesn't violate the binary search tree property. Nodes with values lesser than the nodes key are located at the left, and nodes with values greater than the nodes key are located at the right. This is why AVL tree is also a binary search tree and can be applied in practical tasks instead of normal binary search tree. This is also an improvement over normal binary search tree since it ensures big O log n time complexity for any given movement for insert or any other operation. Next, we continue populating our AVL tree to see other cases. Adding node with key value of 27 will be locating node 27 at the left of node 33. Adding node with key value of 30 will be located at the right pointer of 27. Again, we update heights here. At node with key value of 33, we'll have balance factor of +2 because +1 minus -1 equals to +2. Again, rebalancing is required and it can be done by rotations. In this situation, we have left-right case. In the left-right case, we first do left rotation and then right rotation. This time, let's assume we put hinge at the node with key value of 27. 27 will go down and 30 will go up. As you can see now, we have linear left-left case, where we need to make right rotation. Doing right rotation will give this final result and our AVL tree will be now balanced. Next, let's see right-left case. To unbalance our tree for right-left case, let's add couple of nodes with key values in our AVL tree. First, 130 and then 125. At node with key value of 120, we will have unbalancing which will return -2 as balance factor value. In this case, we need to apply right and left rotation. So we just do the opposite as previous example, but with same idea. 130 goes down and 125 goes up. We have right case now, so we apply left rotation. And as final result, we have a balanced AVL tree. So in this lecture, you learned theoretically what is an AVL tree. As an additional information, I would like to express that even if there are 4 cases in terms of how rotations will be applied, there are only 2 rotation methods such as left rotation and right rotation in AVL tree. If you are confused by this, don't worry. I'll be showing you practically how we have 4 cases but 2 rotation methods in the next lecture. Till then, see you next time. Thank you for your attention.